English will be fine also. Thank you all for having me this evening to share my experiences with creating serverless solutions with Azure Functions. I've created a small solution which I'm using in production right now, and I've come across some things I'd like to share with you all. Anyone familiar with serverless computing, Azure Functions? Yes, yes. AWS Lambda. Also, cool. Google Functions. Good. Well, I'm not very familiar with AWS Lambda. I've used people using it, and it's quite awesome, or so I've heard. But I'm only working on the Microsoft stack, so I'm only focusing on the Azure Functions side of things. So for the people who haven't heard about serverless yet, I'll do a short introduction of serverless. So the name is a bit, disrespecting to the servers, because there are still servers, of course, in a serverless world, because your software has to run somewhere. It's not some distributed desktop system. The thing is, you just don't have to care about servers anymore. This is something we also heard when Microsoft offered a PaaS solution. Also, Amazon offers PaaS solutions, and I guess Google also. So what's the difference? Well, the main difference is the regular PaaS solutions aren't very fast in spinning up and spinning down. There are a couple of other differences, of course, but there's you could see serverless as an evolution of the platform as a service offerings today. Adrian Cockcroft has a nice quote about serverless and PaaS. If your PaaS solution can spin up and spin down very quickly and is meant to run a couple of milliseconds, you can call your PaaS solution serverless. I don't agree fully with this quote, but it's a nice elevator pitch to get people to talk about serverless. And I guess Adrian Cockcroft knows what he's talking about, because he's like the Scott Guthrie of Amazon. So spinning up and down really fast and being able to run small amounts of compute sounds a bit like containers, or at least some people think about containers when they hear this. That's not entirely true, because containers are still running on servers. Also, of course, serverless stuff is running on servers, but containers are somewhere totally different on the technology stack, as you can see in this this diagram. Containers is more like, if IaaS on steroids. You're scripting your network, you're scripting your systems. You do have a small container which is able to do a small amount of compute if you want to, but containers can do a lot of other stuff also. Serverless is also referred to as FaaS, Functions as a Service, which is much higher in the stack and is meant to run when there's some kind of action going on, or it's triggered by something. As you can see, PaaS is somewhere in the middle, and of course you have SaaS solutions like Office 365, which runs in the cloud and you don't care about anything. But you can also, most of the time, not run any code on it. So the Azure Function team has created a small container. I think it was in December, maybe in January, but I think it was December, which has the Azure Function runtime on it, which you can also download and install on your own machines, which enables you to run Azure Functions on your own local on-premises server, and also in containers if you want to. But I don't see any reason why, at least I would do this, because I want to run everything in the cloud, and the least amount of configuration, the better. So I'm only running stuff on the actual function platform, and I would recommend you do it also, unless there's some important reason you don't, of course. Sorry? For testing, well, there are some advantages to running your own local Azure Function Runtime, like being able to configure which assemblies are loaded on the system, which version you are running, if you are very eager to run stuff on premises. So there are some advantages, but if you're already running in the cloud, you could just run the actual serverless offering.
We have this is a microphone. I forgot to explain this earlier. Sorry for that. We will throw this one to you. You can ask a question. That will also be in the live stream correctly. It's fun.
Thank you. There's also, you can run beta software in your actual containers if you want to, like I think it was in January, the .NET Core version 2.0 wasn't supported fully in the Azure Function Runtime, or at least the public Azure Function Runtime yet. But if you use the container, you could just run it and run your functions locally or in the container. So, as I said, there are some advantages, but for most production systems, if you want to go serverless or fast, try to keep on the actual runtime. So, as I said, lots of configuration and just your code. One thing you should remember when going serverless is keep all your functions and all your actual code small and simple. There are a lot of advantages to keeping it small and simple. Of course, it's easy to understand your functions, but also the deployment of your functions will be much faster. As you can imagine, if you have some function which is about 50 megs of stuff, it takes quite some time to deploy this, compile it, stuff like that, which will well, add to the latency of the ramp-up time of your Azure function. So there are, and it also takes in effect the single responsibility principle of a function. Your function should do one thing and do it good. And if you think it should do 2 things or 3 things, please make 2 or 3 functions which, well, do stuff after each other. So for the real life solution I've created, I've came up with it about a year ago because I was eager to do some more talking on meetups and sessions and write some more blogs. And I wanted to use my own custom minified URLs. So I've signed up at bit.ly to create minified URLs. And if you want, you can also point a CNAME record to bit.ly in order to make your own, well, jan.ly/URL. This worked very fine, and I was quite happy with it until they notified me when I wanted to create a new minified URL. I should upgrade to the premium offering of bit.ly. Well, I'm eager to pay for software, at least if I like it, and also for software services. But when I navigated to the pricing page, it told me it cost about $1,000 per month to use a minification service, which is a bit much if you're doing a session once or twice a month, and also for a blog post. So I guess, well, I thought, well, is it hard to write a URL minification service? Because what's actually going on when accessing and creating minified URLs? Well, you get a minified URL and redirect to the actual URL, and you
cost now.
Sorry?
What's the cost if you run it as a serverless?
As a serverless solution, I've made an error when deploying my stuff. I've chosen a couple of technologies, and one of them is the Cosmos DB, and I've chosen to add a partition to the Cosmos DB, for which I needed to have 1,000 DTUs for, well, doing stuff, which cost about $60 per month, and of course the Azure functions, which cost, well, nothing. So it cost 60 euros per month. from my MSDN subscription. But because that's only because I used a partition key, and once I removed this partition key, Cosmos DB only costs about 20 euros per month, and the Azure functions cost, well, nothing, maybe some micro cents. Yeah, and you can do it even cheaper. I'll come back to it later on, but it's actually quite cheap. The only thing you're paying for is the repository. So, but this is what you actually need for a URL minification service. Of course, Bitly offers a lot of other stuff like nice reporting and graphs and insights in who has clicked your links, which is all fun, of course, but I don't need all of that stuff. Googly, yeah, but I'm against Google, so I don't want to use their offerings. Yeah. No, I'm not against Google. I just don't use the products, or try not to use the products. But as you can see, we have one command, and we have one query to do all I want. And this is about half of the acronym called CQRS, which is about commands, which is about queries, and segregating their responsibility. I don't know if you're all familiar with the CQRS pattern, but it's about, well, splitting the reading and the writing functionality of your application in, well, different functional areas. This is a short, well, slide of it. As you can see, you have a user. This user is trying to write something via the write endpoint, which is provided to him. This write endpoint stores some data in a repository. The repository. This repository is optimized for writing, so it should be super fast. And whenever there's something persisted in this update of this write repository, this change is also added, or well, this change is also persisted in the read data store, which is optimized for reading. So completely denormalized, or yeah, completely denormalized data. And once you want to read this data, you just head to the read endpoint, and it should be very fast in reading this data. So that's what CQRS is about in very short layman terms. But as you can see, this is actually quite good for Azure Functions, because we need two endpoints, a command endpoint to write data in a data store, and we have an endpoint which retrieves data from the data store. And I think about all of the Azure Functions solutions you will ever create fits in this pattern. There might be exceptions, of course, but it's a good go-to reference design pattern to go to. And as I mentioned, because I wanted to create a complete serverless solution, I chose to use Cosmos DB as my repository. It was quite expensive, at least for me on my MSDN account, because it only has about 130 euros per month, and spending about half of it on Cosmos DB sounds a bit excessive. But now I've enabled it. Well, now I've changed it to only cost about 20 euros per month, which is better. I've read, I'm not the only one with this idea of creating a URL minification service with Azure Functions. Someone else has created this also, and at least that's what I've read in a tweet last month. And he's used blob table storage, the Azure blob table storage, which is very, very cheap, because when using the blob table storage, you only pay for the data stored. And as you can imagine, storing some characters of a link and characters of a minified link doesn't take up a lot of gigabytes. So I guess he only paid about 1.7 or 17 cents per month for his URL minification service. So mine is very expensive, but at least it's completely serverless. Yay for me. No, but you can make it as cheap or expensive as you want to. One advantage, and that's probably the best technical advantage of me choosing Cosmos DB instead of the blob storage is the Cosmos DB change feed. It's something which has been introduced, I guess, in October or September last year. And what it does, it enables you to act upon changes inside your Cosmos DB. So whenever someone inserts or changes a record in your Cosmos DB, be it Cassandra, Mongo, DocumentDB, GraphDB, I'm forgetting the other one. There are 5 implementations as of now, if I remember correctly. Well, whenever some change occurs in Cosmos DB, it will be reflected on the change feed, which you could see as one big queue, which has changes of the changed records in your database. And you can act upon it. There's a lot of cool stuff you can do with it, and one of them is creating an Azure function and acting upon this. This isn't very useful in my scenario because Cosmos DB is really, really fast. I think Microsoft says it has single-digit response times wherever in the world, so it's a maximum of 9 milliseconds to respond if you do a query on it. Of course, it might actually, if you request a big document, it might take up a lot of time to push it to your app, but at least Cosmos DB will respond very quickly. This is very useful for updating the read repository, of course, because whenever you write something in Cosmos DB, you can update some other repository with an Azure function to update the read database. And the other stuff is interesting also. I haven't used all of this stuff, but I look forward using it in the future if I have time. So a URL minification service, how would you create this in a non-serverless world? Well, it's not very difficult. You just create a web application, connect it to your repository, and be done with it. Of course, this web application has multiple endpoints, the get and the update endpoint, or the create endpoint. So you probably create a ASP.NET Core web API around this, or maybe some nice visual UI to create and retrieve new records. So that's about it. You could make this as fancy as possible if you want to, but this is the minimal viable solution. So in a serverless world, as I mentioned, we will have 2 endpoints, or at least we still have 2 endpoints, but in the Azure function world, we need 2 different Azure functions, one to retrieve the data and one to create the data. In my solution, I've created HTTP triggered Azure functions, which do something whenever someone hits my endpoint. And in my case, the post, I'm using Postman to invoke this endpoint. I'll just post some JSON to this, and it will verify my data and persist it in Cosmos DB. And whenever someone hits the read endpoint, it will just read from the Cosmos DB. Of course, this is the minimum viable solution and isn't very fancy, and doesn't use all of the Azure function goodness which is available, and also not the Cosmos DB change feed. And because I actually wanted to use this change feed, I came up with this diagram just to use a change feed and be more CQRS-like. So as you can see, I'm now using the change feed. I've hooked up a trigger to this change feed to update an Azure cache, which is just a Redis cache, and the get Azure function will only read from this Azure cache. There is one problem with this, is the Azure cache might die and be empty, and there's no way of adding data to this cache yet, or at least not automatically, so I'd have to create a new trigger to update the cache and do stuff with it. So that's one flaw in this design, but for the rest of it, it's quite nice. I just wasn't happy with the stuff below, the post directly pushing data to the Cosmos DB. So what I came up with later. Oh, I'm forgetting. don't use HTTP triggered GET functions if you want to use an actual production system, because Azure Functions has two plans. One plan is actually serverless, which is the consumption plan, and the consumption plan, in the consumption plan you actually don't have to care about servers, which is awesome, of course. One problem with it is it might take some time to spin up. I've seen response times of, well, 500 to 800 milliseconds before my endpoint did something, and that's because Azure has to deploy my binaries to a server, which is somewhere within Azure, deploy it, compile it, making sure the app is responsive, and then actually handling my request. So this takes quite a bit of time. I've seen other people having to wait for minutes before their request was handled, so that's not a very good idea. So if you have you're thinking of an HTTP trigger GET endpoint, either don't use Azure Functions and just use the web app, which could be always on and always responsive, or use the other offering of Azure Functions, which is the app service plan, which isn't serverless because you're deploying your Azure function in the app service plan, which, well, just is a VM. You just don't have to care about the VM that much. And you can just check the mark of always on in the Azure portal, so it will always be responsive and will probably respond within a couple of milliseconds. So that's another, well, not really a flaw, but one thing you have to think of when creating a serverless solution.
Are you making a case to not do serverless?
You should use serverless, of course,
Yeah.
but when having an HTTP trigger with when doing a GET, or a POST also, of course, it could take a couple of seconds before the action is well handled. And if you're using the consumption plan, so if you're using the Azure App Service plan, it should react immediately, but that's not really serverless. That's more fast that's more fast. So you're deploying your functions on a VM. So in an actual production system, I would probably change the GET and the POST endpoints to a normal web application and having all of the backend stuff serverless. Because, well, in an actual production system for a customer, I'd probably want a bit.ly interface with graphs and stuff like that. So you probably want to create an Angular or Vue front end, or the other. So in an actual production system, you probably don't want these endpoints. Don't want to use these HTTP triggered endpoints. But for my solution, it will suffice because I don't care that much of 500 milliseconds delay. Yes?
So you're saying with serverless you cannot create a UI
So you're asking if you can create a UI with serverless offerings. That's something I wondered about a couple of months ago also. And the answer is you can, but just because you can doesn't mean you should. Because what an Azure function is, it's just some code which is running, and if you want, you can just pull back a lot of static files and just respond with HTML or JSON or whatever you want. But it's not meant to do this. There are some proof of concepts you can find on the internet with people just proving you can create a nice web application with Azure functions. It's just not something the team wants you to do. Or yes. Yes, yes. If you're interested in creating a nice front end or a nice, well, something a user can use, just create an app service. with a website in it or something else which can host a website and all of your static files. And having the API serverless is a great idea, but if you actually need user interaction, it's probably better to use the tools which are meant for it. The people which have created this proof of concept of a website using Azure Functions have used the CDNs which are available and responded with some HTML template file which had all of the CDN links in it, and the HTML which they outputted had the data they wanted to return to the user. So it's quite dirty. It's possible, but it's quite dirty. So don't do it. Yeah, like I mentioned, I didn't like the line below, having the HTTP post trigger writing directly in the Cosmos DB, because it's actually doing two things now: validating the input and writing data in the Cosmos DB. So what better way to make this cloud native? Well, add a service bus, because each awesome cloud architecture needs a service bus inside it, or at least a queue. So that's what I did. Having the post HTTP trigger, doing some validation on the incoming JSON, adding some data to it, like the date time created, stuff like that. Posting the object to a queue, actually a topic, because I like topics much more as queues, but that's just me. Having a new Azure function being triggered by data on this queue, and this triggered Azure function will do the persisting of data in the Cosmos DB. So now all is asynchronous, all is working as I want, and it's quite extendable, because when using a topic you can just create a lot of subscriptions for different Azure functions or other stuff to extend your functionality. So if I want to log whenever some minified URL is being created or requested to be created, I could just add a logging Azure function, or do other stuff over here. So I'm happy with this design. For now, I've chosen to skip the above part. Main reason for it is Azure Functions doesn't have native support for Redis cache yet, or at least it didn't have so a couple of weeks ago when I investigated this. And what I mean with a native support is you can't do bindings and you can't have triggers based on Redis cache. There are a lot of triggers and bindings in the Azure Function runtime, which means you can bind to stuff on queues, topics, service buses, event grids, Cosmos DB, blob storage. Well, there are a lot of other things which are available, and also being triggered on a lot of stuff which is happening. Like I mentioned, the change feed, your Azure function will be triggered whenever you register to this. But there's not something for Redis cache yet, or at least not to my knowledge. There has been an announcement for you to be able to create your own custom bindings and custom triggers. I've read about this a couple of months ago. And this sounds awesome, at least for me to create my own custom Redis cache binding and Redis cache trigger. But I haven't had time to do this, so that's why I haven't separated the retrieval of data yet. This also means, these bindings and triggers also mean you don't have to write your own persisting logic anymore. So, because who likes it to create create another new repository, or who likes it to create a file reader or file writer? Well, I've done it a couple of times, and well, now I know how to do this, and I don't actually like doing this. So making use of bindings.
Is it possible to use Redis cache persistence in Azure?
The question is if it's possible to use Redis cache persistence in Azure. Yes, you can use Redis cache for, well, all of the offerings in Azure, and also for Azure Functions. It's also quite possible. You just have to create your new Redis cache client and add stuff to. Sorry? I don't know. I guess it's possible, but yeah, sure. I haven't dug into it much yet, but that should be possible. Yeah. So when using Azure Functions, just use bindings and triggers. So the runtime will do the actual persisting and polling for data for you. Now, how does this look like? Well, whenever you look into this on the Azure docs, you'll see some JSON looking like this, having a function JSON with some bindings inside it, and specifying the type of trigger you want in the case of a trigger, and some properties which are necessary for, in this case, an HTTP trigger. This is the function binding for my get minified URL. So as I said, it's a minified URL. It has a slug, which is prefixed with API. I'll come back to this later on. It's a get method. You can specify any method you want over here, post, put, delete, but a get should only have the get method over here. Authentication level, quite important, because I want all of the world to use my minified URL. I'm using anonymous, but you could add function user system or admin over here, and whenever you do this, you have to specify some bearer token in order to access the function, and of course the name of the variable parameter which will be injected inside your Azure function. So that's about it for an HTTP trigger binding or HTTP trigger. There's also one for having a document DB binding. As you can see, you're specifying the type document DB, the name which will be injected inside your Azure function. In this case, it's minified URL, and you have to specify some additional properties which are unique to the document DB binding. Yeah, of course, because it's an output binding, I want to write to document DB. I have to specify the direction which is out. If you forget to do this, stuff won't get written inside your Cosmos DB. Ask me how I know. So that's about it. And I'd advise not to write any JSON. I'm not a firm believer in JSON. I hate it, actually. So don't do it, especially if you're using Visual Studio, because Visual Studio will do the actual writing of these JSON files for you, which is better because now you don't have to write curly braces all over and making sure the alignment is correct and yeah. So don't write JSON. Make sure you use Visual Studio, and the Azure runtime tooling will do this for you. Now I was planning to start coding some functions now, but there's still some stuff I have to cover, because there's the matter of where will I put the code. Whenever you look online, and most of the time the Azure functions documentation, you will see people writing code in CSX files, which are script files which understands C#. And they have lots of stuff happening in these CSX files, which is awesome, of course. But is this a good practice? I think not. Well, at least not if you ever want to create this for your customer or in an enterprise way, because what you'll get is a lot of duplication of code. I'm not against creating duplicate code because it has its usages. One of the advantages is you can make your code quite simple to read and quite simple to read, and changes are only reflected on the changes you're actually making. But it's still, I think, if you have some code which is doing some logic, it might be better to create a class which is handling this logic, probably in a business layer, or maybe in a business namespace if you want. And what about your favorite libraries? I'm a big fan of using Autofuck and Automapper and well, Log4net and stuff like that in my solutions. Most of the time I'm just download these NuGet packages in my solution, and then I'm going to think of, well, what am I creating? Well, at least I'm having these packages. Do you have to use these libraries inside your Azure functions? Please think about it, because because whenever using these libraries, you're creating some dependencies on some other assemblies, which might be 500 kilobytes, 5 megabytes. Well, they add up, especially if you're using a couple. And as I mentioned, all of these libraries will add up in the total package of your Azure Function solution. And there's a difference in having a solution of 50 bytes or having 50 kilobytes. It will add up to the time Azure Function runtime will be able to deploy, compile, and making sure your Azure Function is available. So be wary of using external libraries. Most of the stuff you want to do can be done quite easy with your own code, and it will make whenever it's your own code, it's probably simpler to read. Not always, of course. And then there's the matter of, should I test? Of course you should test, because, well, we're living in 2018 and everyone should test and we should have 100% coverage. I don't fully agree with this. Of course, I'm a big fan of doing some tests, but only if it matters. Just make, if you have a function which only has some input and stores it inside your Cosmos DB, well, the Azure Function runtime will probably do most of the actual running of your code, and you might have 1 or 2 lines of code inside your Azure Function which does something, maybe validation. Should you test it? Well, depends on how important it is. Most of my Azure functions don't have any tests unless I'm doing something fancy in the business logic. As I mentioned, it might be a good idea if you have some logic to place it inside a new class. And whenever you're creating a new class or think you need some logic inside a new class, well, just test this class, but don't be, what's the English word? Mierenneukerig. You should test everything, because, well, it just adds a lot of time, and an Azure Function run method is static anyways, so which is quite hard to test, at least if you're having some dependencies. So that's what I wanted to tell about this. But other than that, we have some existing patterns developed in the past couple of years. You probably heard of the solid principles, single responsibility, as I mentioned. A function should do only one thing. Interface segregation, awesome, of course, just work with contracts and not with implementations. Dependency inversion, also awesome. You can use this for testing, of course. And I hear some people here thinking, well, he mentioned Autofuck, which is an IOC container framework, of course. Awesome. I'm not using it with Azure Functions, because why use an IOC container framework when the only dependencies you have are maybe 1 or 2 business logic classes which do something? I don't need an IOC framework to have match an interface with a concrete class and only have 1 implementation per interface, which is silly, just to register this. And your Azure Function will probably only have in total 30, 50 lines of code. And of course, creating a container adds up to the ramp-up time, because every time your Azure Function is instantiated, it has to create this IoT container, which takes up milliseconds in best case. So I'm not using an IOC container. I do use dependency injection. What I've done is do something like this. Having a normal default constructor, which I'm using all throughout my code, and having an overload, which I'm able to do some injection and the only time this overload is used is whenever I'm creating a test. You might say, well, I have multiple implementations of my iCosmos client, which is possible, of course, but well, for example, I have a, let's say I have a Cosmos client which connects to the Cassandra implementation and to the Mongo implementation, for the argument's sake. Well, if you have such a scenario, do you actually need both implementations inside one Azure function? Probably not. And if so, isn't it easier just to split it up in multiple functions and having the splitting down, the triggering being handled by your topic? Probably so. So that's why I don't use IOC containers, because there's only one implementation inside all of my Azure functions per interface. So now for the actual creation of the solution. This is the solution I wanted to create: a get Azure function, a post Azure function communicating with a queue, and a trigger Azure function which is communicating or being triggered by a queue and storing stuff in the Cosmos DB. And of course the get Azure function, the HTTP triggered Azure function, will read directly from Cosmos DB because I neglected to create an Azure cache binding. So that's about it. Let's dive into Visual Studio. Let's see if I can duplicate the screens. Awesome. So let's start with a completely empty Visual Studio. Whenever you want to create a function app, just make sure you install the latest Azure Function tooling. So you'll get this nice Azure Function template. That's all there is to it. This will create a new function app solution for you. Oh yeah, because it's a new template. You can choose: do you want an HTTP trigger, a queue trigger, or a timer trigger? Those are the default. You can also choose in the latest version if you want a V1 or a V2. V1 is just .NET Core, .NET Framework. V2 .NET Core, which is still in preview, and it's quite a bit slower today, maybe not tomorrow, but today it's quite a bit slower, so just choose V1 if you want to use this stuff in production. And we want to have an HTTP trigger. I'm using the storage emulator, which makes sure some data is being persisted inside the blobs. Azure functions do need blobs because your code has to be stored somewhere. Access rights, anonymous in our case. You can change this any time you like.
This would all be JSON, generating JSON?
This is creating C# files. Because I'm using Visual Studio, this will create C# files.
Oh, I just thought because the type and anonymous and whatever, I saw that already in the JSON.
Correct. Correct. This will be built into JSON files. Let's just wait for the project to be created. You might have noticed I've mentioned function app. This will get deployed as one big function app, and a function app can contain multiple Azure functions. You should see a function app as one which contains one piece of domain logic, as it says. So in my case, I have a function app which does URL minification, or has a URL minification solution. So in this function app, I'll just create the get, the post, the queue triggered function, and of course later I'll create the Redis cache custom binding and the triggered functions for this. But as you see, let's just do some nice indenting. As you see, I have an HTTP trigger with anonymous, get and a post, and route is null by default. This is what the wizard has done. It has created a function name function1, and whenever I'll run this, I have a function1 which can be called by localhost 7071/API/function1, and I'll trigger this code. Now when I build this, it's ready, rebuild. Okay, I'll just turn on all hidden files, debug. You'll see there's a folder called function1, which reflects the name of my function. And this function1 has a function.json file inside it, which contains all of the binding information necessary to run my Azure function. Also the script file and the entry point. So if you decide I don't want to have my Azure function starting point, don't want to run but want start, you should just change this also to start. Oh. And then you're done, and whenever you build, this will get changed. Oh, automatically. I didn't have to change it over here, of course, because it's generated. And all of this data is being created by the Azure Function runtime because I've set the attribute over here. And that's triggering an HTTP. So I've created a demo, of course. Oh, maybe good to mention. There's also a local settings file, which will contain all of your secret information, like the app.config or the web.config. So your connection strings, your secrets, your other stuff like this will be added to this file, or you should add it. This is for local testing, of course. Yes. Whenever you deploy this, please use Visual Studio Team Services for this, of course, for the adding application settings to your Azure function. But you can change this in a portal, of course, just under the application settings link, I guess. Yes, this is for local testing. And it's called local settings now. I think it was 15 months ago, it was called appsettings.json. So there are some changes, but I think this is quite stable now. It has been called local settings.json for, a year now. So I've created a demo solution, of course. This is my demo. For the sake of time, let's just go to step 3, which is the complete solution I have. And as you can see, probably can see, is I have created a get Azure function, a create Azure function, and a process Azure function. Oh, doesn't work. And a process, just to handle all of the. Just to handle the 3 HTTP triggers, or the 3 Azure functions, the functionality I wanted to have. So the get, the post, and the process. So the get looks like this, an HTTP trigger, much like this, the one we used before, or we saw before. As I mentioned, I have a slug. This is the route, so it will be /API/ my minified URL. I want this slug to be added as a string to my code. You could also have a complex object. Over here, if you have multiple properties which you want to combine inside one complex object. Which is strange in a get scenario because you have a query string, and doing complex objects inside a query string could be hard. So just don't. See, okay. And as I mentioned, my get method wants to read data from Cosmos DB, and in my first attempts I created my own iCosmos DB client and a Cosmos DB client, which did some reading inside Cosmos DB. But a couple of weeks ago, I discovered the DocumentDB attribute and the SQL query parameter it has. So you can just do a select star from, well, my database where the minified slug is slug. So whenever you run or trigger this function, the minified URL enumeration will contain all records inside Cosmos DB which match this criteria, which is awesome, of course, because now I can just delete the Cosmos DB client. I have proof. Over here, it's still, this is my production system. So I have the Cosmos client, and in the get, I'm still, well, I have a handler which does, of course, the dependency injection of the Cosmos DB client. Terrible, terrible, but because of the Azure Function Team, I can just make it simpler. So entering the function, if there aren't any minified URLs, well, not found. If there are, get minified URL, what does this do? Oh, it takes the last. I have some error in persisting my data, so anytime I want to overwrite my minified URL, I'm creating a new record inside Cosmos, so I have to change this later on. So, but for now, I'm just taking the last and create a warning, so I know I still have to fix this. Not very exciting, and when I'm done, I'm just returning an HTTP response with a redirect, of course. So this is my code isn't very well interesting. What's most interesting is the HTTP trigger and the DocumentDB binding, which make all the magic happen. Of course, you have to specify which database and which partition you want to use and the connection string, but that's all very straightforward. All of this stuff is added inside the local settings JSON over here. Of course, we have the create, and if you remember, the create Azure function also is an HTTP trigger, which writes back to the service bus. So let's fix the indenting over here. We still have the anonymous with the post and the route create, and I'm posting a message to this request. I'm posting a request to this, and whenever there's a request, I deserialize it to an object I want, validate the data if it's valid. If not, well, respond to bad request. And if it is valid, what I'm doing here, oh, adding some data like I mentioned, the created date. So not very exciting. You could just skip this if you want to, and create a response. My minified URL will be created with, well, this endpoint. And if I'm lucky, if I've specified this correctly with the correct connection string and the correct, I guess this is the subscription, the topic I want to, the topic name, yes, and the connection name, and it will be written to the service bus topic. Fairly straightforward. I didn't have to do anything for this myself, just create some validation logic. And that's the creation. In order to invoke this, man, I'm just using Postman because I don't need a UI for this. There it is. Not. Move. There it is. So create a minified link. I'm posting to the create endpoint. This is the JSON I'm sending, so the minified slug, .NET meetup Amsterdam, the full URL, .NET Amsterdam. And whenever I send this to my Azure function, it should persist it, or it should create a new record on the service bus. And whenever a new record is added to the service bus, I have this process Azure function which has a service bus trigger. As you can see, this is a service bus trigger, and this is a service bus binding. This is stuff you have to know when you're using Azure functions. I haven't thought of this, I haven't made this up myself. And the documentation is quite clear. So service bus trigger, the queue topic name, the subscription. Yes, you need to manage access rights. I don't know why, because I thought listen would be good enough, but having a listen connection doesn't work, so please use the manage. And of course the connection string to your service bus. You'll get a minified URL. I know it's a minified URL object. If it's not, you'll get an exception thrown in your logging. So I know it's a minified URL because I have bound it over here. And over here you can see I'm using a binder instead of using the Cosmos DB binding again, like I did in the get. Over here you can see I've used the document DB binding in order to add data to Cosmos. I'm not doing this in the process because I don't want to specify secrets inside my local settings or inside my application settings. I want to specify secrets in key vault because it's meant to hold secrets. You can do this, but only for bindings. It doesn't work for triggers. So there's still an issue on GitHub Open, where people are asking, well, please add this binding, add this key vault support also for triggers, so I don't have to specify this connection string anymore over here. But at the moment it's still under review, or at least not implemented. So when using the output binding, I have created a small helper method to do this. Over here I'm creating an iasync collector with a minified URL. So if you want to add data to Cosmos DB, or I think it's also for other repositories you want to write to, like, well, let's say a blob storage also is a repository. You also need the async collectors, or the async collectors. So what you do over here is having a binder. The binder needs to you need to add a document DB attribute to this, which is actually the same as the one over here. It's just so what you're doing over here in the get function is actually exactly the same as doing over here, only just I'm using Azure Key Vault data for binding my data over here. So I've created a helper class secret which does the actual key vault retrieval of settings. If you think of using key vault in your own production system, please make sure this key vault client is created as a singleton, or something which looks like a singleton, because the key vault client and any other client to some other system is quite expensive to create. And if it is thread safe, you should share it across your instances, because even though serverless doesn't, or Azure Functions is serverless, doesn't mean every invocation of your Azure function is hosted on a different server. A lot of the times your Azure Function invocation, your Azure Function instances are being reused, and if not, it's probably deployed on the same server, or it might be deployed on the same server. And if you have this key vault client or any other client set up as a singleton, you don't waste CPU cycles to create all of this stuff again. So that's just a heads up. So that's the processing. And as you can see, I'm not doing anything interesting over here. I'm creating the binding. I could also have used the same binding as in the get method, but I've used something more fancy over here. Creating the new minified URL, which is just doing some mapping to a new object. Not very interesting, but well, necessary, or at least I wanted to do this. And adding it to my output binding, which I've created over here. That's about it for creating an Azure Function solution. So the most important thing you have to remember is just use bindings and triggers, and don't do stuff like this yourself, because bindings and triggers are quite powerful. Any questions on this Visual Studio stuff? No? Good, because I'm already over time. So I had some slides covering deployment. I'll skip this. There's an easy mode in the Azure portal. You can just click deployment options, set this up like any other Azure App Service connected to GitHub, and deploy it. Not recommended for actual solutions. For actual solutions, you should use Visual Studio Team Services or some other build and release CI/CD server. Use an ASP.NET Core template, which has all the steps set up correctly. Create a release pipeline. Deploy it to a slot or not. Direct to production is good enough. Do remember to point to the correct zip package. If you point this to the folder like it is default, it will just deploy the complete folder to your Azure function, which is, well, not very useful, because now you have a lot of files over there which don't do anything. And if you're lucky, you'll see some green checkboxes. In the portal you can see you have deployed this with CI/CD because it's read-only mode. And bonus proxies, very quickly. My URL minification service looks like this: API/minified URL, which is terrible, of course, because who wants API when the URL is minified? You want to have something like this. And this also is terrible because you have the my prefix, which is, well, silly. And that's because A records aren't supported with Azure Functions yet. Which makes sense, of course, because A records point to an IP address, and being serverless, you don't actually have, well, an IP address. They're fixing this. They're busy fixing this, so you can point A records or something like it. I can only imagine the trouble they're going through to support this, but it's coming, but not working at this moment. So how to remove the API prefix? Well, just add a proxy. A proxy is, again, JSON. There's no tooling for this yet, so you have to write your own JSON, which looks a bit like this. So I have created the get minified redirect. That's the name of the proxy. What should it match? Well, it should match a get request with a route slug. So whenever I'm calling my.jdfa.ly/awesome, it should redirect to my.jdfa.ly/API/awesome. You can point this to any other external URL or any other Azure function if you want, but that's proxies. It's awesome. It, I think, is generally available nowadays. It wasn't when I used this, but it's working for over 8 months now. So awesome. If you have any questions later on, feel free to contact me. The complete production code can be found on GitHub. I can be found on Twitter. You can email me, or just follow my blogs, which contain some more information on Azure Functions and other awesome stuff found on Azure. Thank you all.
they scale. For example, if you Google something on big, so to say, then you have already used them. Because as of a few years ago, FPGAs are used to accelerate the big search result pages. And Azure, the Microsoft Cloud, also has FPGAs, although not yet publicly available. But FPGAs are sometimes also found in household appliances like routers. Or if you enter a doctor and got an X-ray or a PET or an MRI scan, then those machines only have FPGAs as well. And the pretty fashionable topic of autonomous vehicles is not without FPGAs either, because self-driving cars, for example, commonly use FPGAs for certain computing tasks, like computer vision even. However, since we are talking about utilizing a piece of computer hardware, you have to be a hardware engineer to actually use them. Also, you eliminate some confusion. Although FPGAs commonly also have visible circuit boards, and they have nothing to do with Raspberry Pis, for example, that also commonly have visible circuit boards. Because Raspberries, well, they are small computers. And FPGAs have nothing to do with microcontroller platforms like Arduino or Arduino even. And that being said, sometimes FPGAs are packaged together or somehow connected together with CPUs or even microcontrollers. So to get back to our train of thought, what Hastlayer does is that it takes a computer program and creates an equivalent FPGA logic. And, well, we are a .NET meetup, so of course not just any computer program, but .NET programs. Specifically what Hastlayer processes are the .NET Common Intermediate Language assemblies. So that means that the original program shouldn't be just C#, for example, but at least in theory, any other .NET language can be used. So programs written in Visual Basic or even Managed C++, or even functional languages like F#, or even scripting languages like Python, PHP, or JavaScript can all be turned into FPGA logic. Right, that's cool, I guess, but why on earth are we doing this? What's the point? And the point is that FPGAs have some unique computing merits. They have some unique benefits that we want to get, of course. So let's have a bit of totally non-scientific, just very crude overview of the benefits or the capabilities of the different computing devices that we commonly have. So let's compare CPUs that we all use every day and GPUs that we most possibly also use every day, and FPGAs that probably we haven't even heard of yet. Well, let's talk about parallelism first, the chart on the left. So how many things can these devices compute in parallel? Well, we know that CPUs commonly have the desktop ones 4, 8, maybe 12 cores, and probably twice as many logical cores. And server CPUs can have 32, 64 cores, but that's about the top of it. Now, GPUs in orange are on the other extreme of this scale, because GPUs are very highly parallel devices. They sometimes have thousands of little processing cores that all work in parallel. Now, FPGAs, the chart in gray, are kind of a middle ground here. FPGAs don't really have cores, so to say, but although that's not entirely true, but the level of parallelism you can get from an FPGA is somewhere in the order of magnitude of hundreds, sometimes thousands. This, of course, well, all of these, of course, highly depend on the specific application and the specific device. Now, let's talk about the complexity of programs that you can run on these devices, the chart in the middle. Well, with CPUs, you can run pretty much anything. So as long as it's a program, you can run it on a CPU. Well, sometimes with emulation or jumping through hoops, but in the end, you can run it. Well, with GPUs, it's a bit more limited. Again, GPUs are on the other end of the scale here. Because on a GPU, you can't just use any control structure, any data structure. And the programming model there is much more limited. Well, with FPGAs, it's again kind of in between. although you can't really program an FPGA, but if you take a high-level tool like Hastlayer and turn a piece of program into a piece of FPGA logic, then what you can do there is usually somewhere in between. Now, lastly, let's talk about power efficiency of these devices, the chart on the right. So how many things can be computed with 1 watt of power? And CPUs and GPUs are roughly on the same level here, again highly depending on a lot of factors. But FPGAs really shine, because FPGAs are very power efficient devices. And the reason is that with an FPGA, you basically get an application-specific processor. Because you can configure an FPGA to do just what you need it to do. There is no instruction set to handle, like in a CPU. There is no operating system to run, and no other programs to run. It will just run on the bare metal what you need it to do. And because of that, and because FPGAs are also very low power devices with slow clock cycles, they can be very power efficient. Right, that's fantastic, but there is a huge downside, and that's that it's quite hard to utilize FPGAs. Because, well, programming a CPU is easy enough. Programming a GPU is a bit harder, but you can manage if you are a software developer. But using an FPGA is something completely different. Since there you don't write a program that will run on some kind of processor, but you create a piece of hardware. And therefore you need to think in terms of clock cycles and logic gates and wires. It's very different from software. But with high-level tools like Hastlayer, we intend to bring this complexity down onto the level of software development. And I think we are mostly there. So to summarize, what we aim for here is to get the benefits of FPGAs for all of our software developers. So if you have an application that is highly parallelizable and is compute bound, then most possibly with FPGAs and with Hastlayer it can be made faster. And at the same time, you get this with a higher power efficiency. So you can do more stuff with less power. And now, if you are thinking about applications that run on compute clusters on hundreds or thousands of computers, power efficiency matters a lot as well. And, well, it's still software development mostly as usual. To give you a bit of an idea of where FPGAs are already used, not with Hastlayer in every case, but just generally, here are a few examples. For example, the area of artificial intelligence and machine learning commonly benefit from FPGAs. FPGAs are already being used for training as well as for execution. Image and video processing are typical use cases where there is a high level of parallelization. And because of that, FPGAs can have a benefit just as with computer vision. Now, algorithmic trading on stock exchanges, or rather high-frequency trading, is where FPGAs are also used, because there you need microsecond level latencies. So you need to do a trade on the stock exchange within microseconds after receiving some data. And by putting FPGAs directly on the network, they can achieve that. Data compression is a more I/O-bound task, not just purely CPU-bound, but still FPGAs can be used there. Now, I'm mentioning cryptography and cryptocurrencies together because FPGAs can be used there for hashing, which is the mostly compute-intensive task in these areas. But not Bitcoin mining anymore. That ship has sailed. And due to FPGAs being low-power devices, embedded systems like IoT devices or robots can also use FPGAs, and FPGAs are already being used here. Right, so a lot of talk until now, and let's see a demo, and let's see how you as a software developer could use Hastlayer in your application. What we will see now is, of course, Visual Studio, but this time we don't run it in Visual Function. function, but rather a highly parallelized algorithm with Hastlayer. Because what we see here, as the name also suggests, is well a highly parallelized algorithm. Specifically, what it does, and this is just an example. This is not something really useful, but rather what I will show you here is kind of an exaggerated example of the class of algorithms that are especially suited to be accelerated with Hastlayer and with FPGAs. And what it does here is that it first takes an input number and then starts tasks here. And I would guess that everybody is familiar with tasks here from the .NET Task Parallel library. But just as a recap, if you start a task, then you will basically use an abstraction over threads. So eventually, a thread will be selected from the .NET thread pool, and the .NET task scheduler will schedule this task to be executed on a CPU thread. And how many CPU threads are there, or what the level of CPU level parallelism is? Well, it depends on the number of cores of the CPU itself. I have an Intel Core i7 CPU in my machine. It has 4 physical cores and 8 logical cores. So we will get an actual hardware level parallelism of pretty much 8. There will be more threads, of course. But we will start 280 tasks here. Now these 280 tasks will still execute on these 8 logical cores in my machine. But when we turn all this into hardware with Hastlayer, then on the hardware we will get 280 little cores that were rolling parallel. So on the hardware, in the FPGA implementation, we will have an actual hardware level parallelism of 280. And this is supposed to give us a performance advantage, of course. We will see. Now, what happens in this task, by the way, and is here. This is some simple logic. There is some conditional logic inside, which is executed 10 million times. And then the result is returned back. Now next, we wait for all these tasks to finish. And once that happens, we sum together their results. And this sum will be the output of the whole algorithm. So as you can see, pretty simple. It doesn't have too much point, but it's just an example. And by the way, all of this is up on GitHub. I will show you the link later. So you will be able to if you are interested. But for now, let's also run it. And actually, I have an FPGA prepared here. I hope you can still see my webcam, because what I'm showing you here is an FPGA port. I have hooked it up to my machine by a USB cable, which is here. And this will be used to execute this algorithm. Because what happens in the background is that Hastlayer creates a hardware implementation, and once that's done, that takes a few seconds, and once that's done, it will start to communicate with the FPGA and execute this algorithm 3 times. So let's see the results. Here we can see that executing this on the FPGA took about 300 milliseconds, give or take. Actually, if you take a closer look, it was almost exactly the same amount of time each time. And again, the reason is that on the hardware there are no noisy neighbors, so the execution time can be pretty much deterministic. Now, it took 300 milliseconds on the hardware itself, but if we also take into account the communication round trip between the host PC and the FPGA port, then the whole thing was, well, just below 400 milliseconds. And the reason of the quite big difference is that this is a relatively low-end board. It's a cheap development board. It costs around $300 US. And it was easy to start with, but it's not really a production level board. part of the reason is that it only offers slower communication channels like visual serial via the USB cable. So with bigger, faster FPGAs, we can cut down this latency a lot. But even with this low-end FPGA port, it was much, much faster than on the CPU. Because on the CPU, the whole thing was just below 3 seconds. So about 400 milliseconds, where there's 3 seconds. There is one order of magnitude difference. The FPGA was about 10 times faster. Now, of course, this wasn't a very scientific measurement because my CPU is doing a lot of other things at the time, and I'm also screen sharing. But even if we took this away and we would run the same thing on an idle CPU, it would be below 2 seconds. So this kind of should show you or shows you that what's possible with FPGAs and with Hastlayer if your application is highly parallelizable. There are other examples as well. It's up all on GitHub, but we won't go into more details here because, well, we don't have much time. So let's get back to the slide deck. And let's also wrap up. First of all, what's next in Hastlayer? Or what's next in for Hastlayer? Because this is the state of the project, but we are not stopping here, of course. Well, for example, we are working on field testing the system. So we want to gather real-life examples that we can test Hastlayer with. And for example, one of the things we did is that we engaged into a partnership with the Wiener Research Center for Physics, which is part of the Hungarian Academy of Sciences. And those are some pretty smart guys, mostly theoretical physicists. They also work with CERN. And what we want to check with them is how scientific computations can benefit from Hastlayer. Actually, we tried out one algorithm. It's also included among the samples on GitHub. And it's very power efficient, but it's not faster yet than on a CPU. And part of the reason is that our current FPGA is just too small and too slow for that more complex algorithm. And we are also working on floating point support, because embarrassing as it sounds, Hastlayer doesn't have floating point support yet. So you can't write double and float, for example, as we do in normal .NET code. And this is something generally what FPGAs struggle with. So we needed to do something. And what we are working on is supporting a floating point number type called POSIT. Now, this was invented by a mathematician called Dr. John Gustafsson, and it promises to be better than even double and float. But still, it's usable pretty much in the same way. And it's also more FPGA friendly. And we have already done it mostly. It mostly works. We just haven't really released it yet. And by the way, this is also an interesting thing, that with Hastlayer, you can write your own number type, and basically within 10 seconds, you can get hardware support for that. Because otherwise, your CPU won't know about that number type. But with Hastlayer, you can attach an FPGA, and now you basically have a processor that knows your number type. We are also working on making Hastlayer high-performance computing ready. As mentioned, the only FPGA we support right now is this slow development board, which is not enough, of course. But we are working on supporting bigger, faster cloud FPGAs that will be dozens of times better. And it seems that FPGAs are coming into data centers as well. Probably you have heard that as of recently, the Amazon Cloud, AWS, also have FPGAs. You can just purchase virtual machines with FPGAs inside them. Azure already has FPGAs, as I mentioned, although not yet publicly available, though I think they will soon be. And then we will be able to run Azure functions on FPGAs as well. to refer back to the previous presentation. And Intel is betting on FPGAs as well. Because as of about 2 years ago, Intel has acquired the then second largest FPGA manufacturer called Altera. And now Intel is an FPGA manufacturer. And what they are working on, for example, is building together a Xeon server CPU with an FPGA. And well, it's an ongoing process. But if you think about it, that's quite a logical step. Because we can't really make CPUs faster anymore. We have long reached the maximum of clock speeds, and nowadays we are reaching physical limits of how many transistors can fit on a chip. But with FPGAs, you can kind of cheat the system. Because if you put an FPGA core into your CPU, then you can make your CPU execute applications faster without actually making the CPU faster. Since you get an FPGA, with the FPGA, you get an application-specific CPU core. So quite interesting, we will see what Intel can somewhere. Now, if you like this, and I really hope you did, then go check out the SDK. Here is the GitHub link I mentioned before. You can use Hastlayer for free. And we are at it because FPGAs are coming. I would say that with FPGAs, we are roughly where we were with the GPUs maybe 5-8 years ago. Because if you can remember, programming a GPU a while ago wasn't that simple like it is today. You couldn't just fire up an SDK and program right away. Of course, video game developers program GPUs, but if you as an everyday software developer wanted to run some general purpose computing, general purpose applications or computations on a GPU, that was quite hard. But due to gradual improvements, nowadays GPU programming is fairly straightforward. And I think the same thing is happening with FPGAs. So it's still a playground of specialists mostly, but very rapidly you'll get another computing device for all of our software developers that we can utilize. So that was it. Thank you for your attention. Shoot me an email if you have a good use case for Hastlayer. I would love to hear about that, and I can help realize it. And the SDK is up on GitHub as mentioned, and you can check out hastlayer.com for further info, or lonwig.com if you are curious about the curious people behind Hastlayer. And now we can have a little discussion until we have time. If you have any questions.
So anyone that has a question?
I was wondering if you can explain what happens between the moment.
Sorry, could you go closer to the microphone, because I can hear you talking, but I can't understand anything.
I will repeat the question in a moment.
Can you explain what happened between the source code when you had it on the screen, and then you send it to the board, and you got the results back? What happens in that process?
Can you explain, you had the source code on screen, and then you send it to the board, and what happens in between?
Yeah.
Could you hear that question?
I'm not sure I entirely got it, because I couldn't understand everything. So, you said that I had source code on my screen, and then what was the next?
I think you compiled it and you run it. What happened exactly? What's the steps?
Is the question was how did I run this?
Yeah.
Okay. So something I haven't shown you due to the lack of time is that this is part of this class here. Okay. Yeah. This class here is part of a console application. This console application among the samples. And this console application also has a main class, of course, and here is where Hastlayer is orchestrated. So the parallel algorithm sample is a piece of code that you run the hardware, but here is where you start the whole thing, and here is where you start up Hastlayer, and that leads to generate the hardware. I would just emphasize two things here. First of all, here's the generate hardware method call. Now, this is where we pass an assembly to Hastlayer, and this is where it generates the hardware code. The hardware code is also something by the way you can check out on GitHub. If you are interested, although it's quite frightening. It's very long. And now this is where the hardware code is generated. This is something that also happened when I started the demonstration. And next, the second thing is that here is how you execute the hardware implementation. As you can see, basically what happens is that you just call the run method on your objects. So that run method that's here in the parallel algorithm sample. And the reason why this works is that on this line here, we have taken an instance of this parallel algorithm class and wrapped it into a proxy with Hastlayer. So what basically this allows Hastlayer to do is to hijack method calls. So this way, this object or the object in this variable seems like the usual parallel algorithm object, but when you call run, Hastlayer will take over and transfer the execution onto the FPGA that I have here. So all this is pretty much seamless. There is one further step that I haven't shown you, and that's the generation of the FPGA configuration from the hardware code that Hastlayer creates. That takes some additional time in the background, and so I didn't want to take the time of the demonstration with that here. But that's something you have to wait for, and not something you have to directly deal with. Does this answer the question?
Yeah, yes.
Okay, great.
Any more questions? Zoltán, thank you very much for the presentation.
Thank you for having me, and have a nice remaining evening.
Thank you, you too.
Bye everyone.
Bye bye. So what you can do now is you can, if you still want to, then grab another drink and go to the room up front and have a chat with everyone. Or if you need to go, you can.
That's good to hear.